back to the vaWT simulation tutorial in ANSYS Fluent. I'm Mohammad Reza Timouri, and in this part, we're going to set up solution animations so we can visually track changes during the transient simulation. This is a powerful way to observe the behavior of velocity, pressure, or other variables over time, especially when analyzing rotating machinery like wind turbines. Now, let's go through each step, and I'll explain why we do it and what each option means. From the Fluent menu, go to Solution, then Calculation Activities and click Solution Animations. This panel allows us to define what to animate, when, and how to save it. Set Record After Every equals 1. We want to capture the simulation results after every time step so that our animation appears smooth and continuous. If we record every 5 or 10 steps, we might miss important flow changes between steps. Choose Time Step. This tells Fluent, record the animation at each time step, not at iteration steps, or based on other conditions. This is essential for transient simulations, where time-based behavior is critical. Set Storage Type to HSF file. Choosing HSF hierarchical storage format allows efficient saving of large animation data. It's a compact and readable format used by Fluent for post-processing purposes. Click New Object and select Contour. We're visualizing how velocity changes in the domain. A contour plot provides a color-coded map that makes it easy to identify high-speed and low-speed regions in the flow field. Now, we should change contour panel settings. Select Contours of Velocity. Velocity. Magnitude is selected below. This shows the total speed, not just in one direction, which is best for visualizing rotating flow behavior. Tick Filled. Displays smooth color shading instead of line contours, which makes it visually clearer. Deselect Global Range. By default, Fluent scales contour colors to the maximum and minimum values across all time steps. We disable this so we can set a fixed range and better compare changes. Deselect Auto Range. Prevents Fluent from dynamically adjusting the color range at each time step, which can distort the interpretation. Deselect Clip to Range. We don't want values outside the range to be cut off. We want to see the full picture. Set minimum equals 0 and maximum equals 20. This is based on our expected velocity range, wind speed and blade speed. Having a consistent scale across frames helps in comparing flow intensity. Deselect all surfaces. In 2D simulations, Fluent plots results on all cells by default. We don't need to pick specific surfaces unless we want to limit it, which we don't for now. Click Display to preview the contour. Close the contour panel after preview. Click OK in the animation panel. Now Fluent knows what to record, when, and how. Animation setup is complete. Alright, continuing from where we left off now that all animation and mesh motion settings are finalized, the model is ready to run. First, save the project to avoid any data loss. File, then select Save Project. This ensures that your transient setup, mesh motion, contour settings, and animation sequences are securely stored. Next, we set up the transient solver parameters. Time step size. Set this to 0.005 seconds. This defines the time resolution of our simulation. A smaller step gives us more accurate results but takes longer to compute. Number of time steps. Enter 314. This specific number simulates exactly one full rotation of the wind turbine blades at 4 radians per second. Why? Because 4 radians per second means one full revolution, 2 pi radians, takes 1.57 seconds, and 0.005 multiple 314 equals 1.57 seconds. You might ask, do we need to initialize again? No, we don't. Since we use the solution from the moving reference frame MRF setup, Fluent continues from those results as the initial condition for our sliding mesh simulation. That's one of the advantages of this two-step setup. Now, go ahead and click Calculate to begin the simulation. Fluent will solve the unsteady flow field as the blades rotate, capturing interactions, transient wakes, and real-time effects that the MRF method couldn't. Now that the simulation has finished running successfully, let's move on to the exciting part: post-processing the results and reviewing the animation. Go to the Results section, then click on Animations, Playback. Here, you'll see the animation window. Simply hit the play button to visualize how the fluid flows around the blades as they rotate. This gives you a dynamic view of the transient behavior, something the MRF method couldn't fully capture. You can also export the animation. Just go to Write Record Format, choose MPEG, and Fluent will generate a video file in your working directory, perfect for presentations or reports. Now, let's briefly compare this method, the sliding mesh method, to the moving reference frame, MRF approach we used earlier. MRF is a steady-state method. It gives you a quick approximation of how the flow behaves around rotating parts, without simulating motion over time. It's faster and simpler, especially useful in early design stages or when you want a basic understanding of flow patterns and performance. But sliding mesh is a transient approach. It simulates real rotation over time, capturing the true interaction between blades and flow, including unsteady wake formation, vortex shedding, and asymmetric effects. It's more accurate but also more computationally expensive. So which one is better? Use MRF when you need quick insight with limited computational resources. Choose sliding mesh when detailed transient phenomena are important, like in wind turbine studies, fan blade interactions, or pump designs. Don't forget to save your project at this point. File greater than save project. This ensures all your hard work, including simulation data and animations, is stored properly. We've learned how Fluent can handle rotating regions dynamically without needing to remesh every time step. This is thanks to the use of non-conformal interfaces, disconnected cell zones that Fluent treats as rigid bodies. And remember, if the geometry deforms or changes shape, Fluent also offers the dynamic mesh model to handle such advanced cases, automatically adding or removing mesh cells where needed. And with that, this project has come to an end. In this final part, we completed the sliding mesh simulation for our Vertical Axis Wind Turbine, vaWT, in ANSYS Fluent. Here's what we did. We configured the transient solver using a time step of 0.005 seconds and running it for 314 time steps to capture one full rotation. We set up solution animations using contours of velocity magnitude, customized the display range, and previewed the animated results directly inside Fluent. We compared the sliding mesh method to the MRF approach and explained how sliding mesh gives a more accurate, time-dependent picture of flow behavior, especially for rotating machinery. I should say that if you'd like, you can go to the report section and extract valuable data, like force and moment plots, for deeper analysis. Thank you so much for watching and following along. If you found this series helpful, please leave a like, drop a comment, and subscribe to support the channel. Your support truly motivates us to keep creating more engineering content. See you in the next project. Take care and goodbye.